Today's topic is electric current. So today we are going to start with the electric current. So flow of charge and how fast that charge moves through a conductor, that gives us the current or electric current, we may say. So through any conductor, when electrons are moving, they are the main charge carriers, right? They are the main charge carriers, and the flow of electrons per unit time through the conductor, that will give us the rate of flow of the charge. Means, and the current is denoted by I, which is equal to total charge. Charge, we know it is denoted by Q upon, that is, we want to find the rate of flow of charge. This is divided by time t. That gives us the I is equal to Q by T, which I is current. Current is equal to charge flowing per unit time. And units of current are ampere. This is denoted by letter A. A is equal to unit of charge is coulomb and time is second. So 1 ampere is 1 coulomb per second. That means if a charge of 1 coulomb is flowing through a conductor in 1 second, that means 1 ampere current is flowing through it. And this charge is due to the number of electrons. This is equal to number of electrons. Say n number of electrons are flowing and each electron is carrying a charge of E. Then you can also be written as Ne and upon T. So this is equal to upon T. So I is again equal to Ne by T, where E is charge of 1 electron, N is the number of electrons, and T is the time. And charge on 1 electron jo hai, this E is equal to, we have 1.6 into 10 raised to power minus 19 coulomb. Sorry, let me just. $19 coulomb. So there are 1.6 into 10 raised to power minus 19 coulomb. This charge is on 1 electron. And if we are asked how many electrons can be there in 1 coulomb of charge, we can simply find out by dividing 1 by, if we are given charge of 1 coulomb and we want to find the number of electrons into it. So what we'll do 1 divided by charge of 1 electron, that is 1.6 into 10 to the power minus 19, which gives 6.25 into 10 to the power 18 electrons. That's the number of electrons which are flowing per second to give 1 ampere of charge. Right? Then is the topic current density. What is current density? So current density is, current density, right? Current density is, this is denoted by, so this is denoted by J. J equals current upon area. This is current upon area, right? So current density जो है, it is a vector quantity, and its direction at a point is the direction of motion of the positive charge at that point. SI unit of current density is ampere per meter square. Ampere per meter square, and its dimension will be A, L. So units are this is ampere per meter square, and dimensions are A, L raised to power -2. This is the dimensions, right? Then, so now we are going to find the most important thing in this is, which is the drift velocity of the free electrons, mean free path of the free electrons, and the relaxation time. So what is drift velocity? First of all, let us understand. Suppose we have a conductor over here. So let's say it's a conductor. Connected to battery. Fine. So this is source P voltage, and let's say length of this conductor be L, right? And A is its area of cross section, right? And let's say here we have a electron minus, right? And its velocity is, it's moving towards this direction, fine. And when a electron, one more will show minus. This is moving in this direction. Let's say it's moving with velocity Vd. Vd. So its electric field is from, so since this is the positive end, so electric field will be from positive to negative. So let this be the electric field. Right? So we have considered free electrons which are moving in a metal. They they yes. Okay. Now electrons are free to move in this conductor. When electrons are moving, they will be colliding with each other. Fine. And after colliding with each other, they may change their direction also if they are moving randomly. But when this is connected to some source of battery, then electrons will be aligned to move in one direction. Right? Electrons are moving in the, say, against electric field, right? The average distance which is moved by any free electron, and during the motion, the free electron will be colliding with the ions again and again, and after each collision, their direction will be changed. Like when we are in a football ground, suppose players are hitting the football in any direction, but there is a, suppose this is a goal post A. Here we have a goal post, say A, and this is a goal post B, and players are trying to move the ball. Players of team A will tend to bring the ball towards goal post at B, and players of B will move the ball towards goal post of A. Fine. So, and when they are hitting the ball, every time there is a collision, the ball changes its direction, its velocity is also changes, acceleration is also change. If velocity changes, there will acceleration. And between any two successive collisions, there is a free distance. There is a distance between where the ball is moving straight line. The ball is moving in a straight line. So similarly, in a matter when electrons, they are colliding with ions again and again, and after each collision, the direction of the motion is changing. And the average distance moved by, average distance, we will say, moved by free electron between any two successive collisions. That is called the mean free path. Mean free path, right? And average time interval between any two successive collisions, that is called the relaxation time of the, that is called the relaxation time of the electron. We'll find all this, right? So direction of the mean, direction of motion of free electrons, they also change after every collision. Hence, the average thermal velocity of all the free electrons will be zero because they are randomly moving in any direction. So their average velocity might be considered as zero. Suppose it means that if there is no net motion of the free electrons in any particular direction, but if an imaginary plane be drawn, as we have taken this imaginary plane, right? The rate at which the electron pass through the plane from right to left at the same time as they will pass from left to right to left, and the net rate means zero. So when we connect this metal plate to the battery, which has a potential difference of V, fine. So V is also equal to ED, or ED is L. We may write V is taken as V is equal to E, which is electric field, and this is L. EL between the ends of the wire. Fine. As a result of this potential difference or electric field, each electric field will electron will experience an electric force. Fine. So that force, which will accelerate the motion of the electron in the direction opposite to that of the field. So electric field is moving from B to A, as shown in the here. E is electric field. Electrons are moving opposite to this. Right. The magnitude of magnitude of acceleration produced by the electron, that is equal to what? So we can write it as A. So this is A force upon mass. Right? Force upon mass. And this force, this is equal to electric field here. So we can write Q times E. Or let us say that this is Q times E. E is the electric field. Q is the charge on each electron. Right? So Q times E will give us a force acting on charge, say M. And what is the value of E? It is VL. So we may write here, this is, this is equal to Q is VL. So that means equal to Yeah. Two E की जगह we can write V by L. Q by QV upon this M, and this is L, V by L, right? So this is the accretion. So this accretion, which is produced in the electron, will drift the electron slowly in the direction of the force, right? And acquires a component in addition to velocity, right? And the velocity of electron as a result of drift does not increase continuously because it is colliding again and again with the positive ion of the metal, and it will lose whatever kinetic energy it has gained because it's moving some force. It will gain kinetic energy also. That kinetic energy will be lost whenever it's applied. And the potential difference of the battery, it does not provide an accelerated motion to the electrons, but simply gives them the drift toward that. That is a small constant velocity of order of, say, few millimeter per second, fine, along the length of the wire, but opposite to the electric field. So this average velocity is called the drift velocity of the electrons. So now we find the formula for this drift velocity, right? So that is drift velocity let's say tau1 tau1 is the relaxation time for the electron, right? So in this time, the electron accelerates under the effect of applied electric field from velocity, say 0 to, say, velocity v1. So because this is the relaxation time, fine, in which the electron is accelerating, that means it is not facing any collision, right? Between two successive collisions, we can say. So tau1, this is equal to relaxation time So this is relaxation time. And in this time, velocity increases from v is equal to, say, 0 to 0, 1. v1. Velocity is from v1. Now, using equation, we have v is equal to u plus at. This is we have v1, initial velocity was 0, right? So A is the acceleration and tau is the relaxation time, A tau 1. Similarly, these expressions will hold for other electrons also. And let's say there is an average of n electrons. So fine. So let's say n electrons are there. Electrons are there. So we have V1 plus V2 plus V3 plus till say n number of electrons are there. So we have Vn is whole divided by n number of electrons, right? This is equal to, we may say, because the total velocity remains zero, average velocity, which is say initial velocity of all the electrons is zero. So 0 plus A, right, into time, relaxation time will be average for all, that is tau 1 plus tau 2 plus tau 3. This is plus tau 3 plus tau n, right? Whole divided by again n. Now, so this average velocity is considered to be d, this one, right? So we can have V1 plus V2 plus V3 Vn whole upon n. This is equal to Vd, right? And this term, this is the relaxation time. So let this be equal to tau. Fine. Now we can say Vd equals A tau, right? Now the value of A was previous page we have found the value of A is QV m by L, or we can write say QE by m. So we can substitute this value over here. This is Q E by m into tau. This is what the drift velocity, right? The formula for the drift velocity is Q E m by tau, right? You can write instead of E, we can also write V by L. So that can be used as Q E is V by L, V by L into m. This is m, right, into tau. This is the formula for the drift velocity. Now, what is mobility of electrons? Mobility of electron means in a solid state, the electron mobility characteristics characterizes how quickly can electron move through a metallic conductor or through semiconductor when it is pulled by some electric field. Fine. So we know drift velocity is Vd. Vd is equal to A into tau, right? And what is A? That is E. So QE by M. Fine. But drift velocity, we have just found the formula as QE M by tau, right? And if this remains constant, E, and which Q is charge, then tau, relaxation time upon mass. If this remains constant, right, then Vd jo hoga, it is, let us denote this by another factor, say mu E. If it is denoted by, let's say, factor Q tau by M is equal to constant, fine, and let the value of this constant be mu E. See if this is constant, right? Then we have Vd, drift velocity, is equal to mu E times electric field, right? Mu E times electric field, which gives us mu E as Vd by E, that is drift velocity per unit electric field is the mobility of electrons. We can say the drift velocity per unit electric field gives us the mobility of electrons. Fine. Then what is the relation between the drift velocity of free electrons and electric current? So it's very again important. It's really tough to write on this board now. Relation between drift velocity of free electrons and electric current. We'll find this. Right? Now we know that the strength of electric current in conductor that is measured by the magnitude of electric charge flowing per second through a cross section of the conductor. And suppose the ends of the metallic wire, they are connected to battery. Fine, they are connected to battery. So that an electric field E is established in the wire. And the strength of the current in the wire is given by the relation. We have I, this is equal to Q by T. I is equal to Q by T. right? I is equal to Q by T. Right? And suppose area of cross section of the wire is A. Area of cross section is A, and the number of free electrons of the unit volume of the wire is N. So we have, say, A be the area of cross section of the wire. Right? And the number of electrons per unit volume we say N. So N is the number of electrons per unit volume, right, of the wire. Then the number of electrons passing per second per second through a cross section of area will be equal to, so then the number of electrons passing per second through a cross section of the wire will be, say, N into A times into VD. V, say, D. So I'll write here VD. That's our drift velocity. VD is the drift velocity. Fine. So Q will be the charge passing through, so charge passing through the cross section, right, through the cross section of the wire in time t seconds. This will be कितना आएगा बेटा? So total charge Q is equal to C N A VD, fine, into a Q charge on one electron, or I can replace this Q by E charge on one electron, right? And current will be, this is charge, fine. So current I is equal to Q by T. Q by T, right? So we have this NEA charge Q by T, and current passing per second will be, I may write as current I is equal to N times E into A into V into D, or you can remember it as NEVA, right? So that is the relation between the drift velocity VD. This is equal to I. Fine. And if we replace this VD by mu times, say, mu E, right? This mu E, then current will be equal to N E A mu times this E, right? Mu times E, where mu is the mobility of the electrons. Fine. Then electric resistance. Ma'am, typing is better idea, I suppose. Hello? So before going that, let's start the Ohm's law. Ohm's law, what does it say? So Ohm's law gives us the relation between the this potential difference and the current, right? So according to this, if we keep the temperature constant and other physical quantity constant, right, of the conductor, then the then whatever the potential, the current flowing through it is, or if there is no change in the physical state, Ohm's law states that if there is no change in the physical state, right? The physical state of a conductor, such as temperature, fine. Then the ratio of the potential difference applied at its ends and the current flowing through it remains constant, right? That is, we say V by I equals to constant, and this constant is called resistance, which is V by I is equal to R. R is constant, that is called the resistance. That's called the resistance. And the factors on which the resistance depends. Resistance is otherwise the obstruction which is caused to the flow of the electrons flowing through the conductor, passing through the conductor, right? And the units of resistance is ohm. That's the omega symbol for that. Ohm, denoted by omega, right? So 1 ohm is equal to 1 volt per ampere. That's the resistance. If we draw a graph between these two lines, let's say this is the graph we are going to draw. That's going to be straight line. This is I. And here it is, say, V. If the graph is drawn between current and I, we always get a straight line. And those conductors which obey this Ohm's law, they are called the ohmic conductors. And those which do not obey, like metals, they are the ohmic conductors, they obey the Ohm's law. And those which do not obey this Ohm's law, they are called the non-ohmic conductors, like diodes, right? Like they are the diodes. So, and the reciprocal of this resistance is called conductance. So reciprocal of resistance is called conductance. Right? Is called conductance. And the units of conductance is mho. Is mho or ohm inverse. Say ohm inverse over -1. Right? Then the dimensional formula for the resistance, you may write here it's not so important. We can leave that for later on. Factors on which the resistance depends. Okay. Resistance depends upon so length of the conductor, it is directly proportional to it. Or we may say resistance of a conductor is directly proportional to length of the conductor. Is inversely proportional to the area of cross section of the conductor. Right? On combining, we have say, then it also depends upon the temperature. It also depends upon the nature of the material. Right? It depends on the temperature. As well as the nature of the material. Good conductors have low resistance, high conduct, and insulators have high resistance. And when we increase the temperature, the resistance also increases because in a conductor, not in a semiconductor. Semiconductor, it happens that when the temperature is increased, the resistance decreases. In case of conductors, when temperature increases, resistance increases because number of collisions increases. Fine. So on combining these two, R can be written as, so this is the there's a symbol called rho. This is rho, let's say. Rho, say, L whole upon A. This rho is called the specific resistance, or it is also called the resistivity of the material, as it's the characteristic property of the material. Conductors have low value of resistivity of the order say 10 raised to power minus 4 to 10 raised to power minus 8 ohm, and insulators, they have high value of resistivity up to 10 to the power 8 ohms. Metals have low resistivity, and these insulators, they have high resistivity. So this rho is equal to, we have RA by L, RA by L. And the units of resistivity are ohm meter. So reciprocal of resistivity is the conductivity. That's the conductivity. Right? Now, we can also this calculate, or we can find the Ohm's law in terms of electrical resistivity and conductivity. So let's say L be the length of a conductor and A be the area of cross section of a metallic wire. So when potential difference is maintained across its end, the acceleration experienced by the electrons of mass m will be kitna? That is equal to say L. Let L be the, let say L is the length of the conductor, and A is the area of cross section of the conductor, right? So A is the acceleration, right, experienced by the electron of mass by the electron of mass m. Right? So A will be equal to F by m. We have F by m. F is equal to Q times electric field, that is QE. This is by m, and E we know it is V by L. So this can also be written as Q V upon ML upon ML. This is what the expression is, and we know the drift velocity. Drift velocity we have VD. This is A tau. A, let's write T tau. A tau 80, fine. And we know that drift velocity and current, they also have a relation from current, and from current drift velocity relation, we have VD as I upon A N. This is E is the charge on electron. So I can also change here from Q to, we can write E also. Let's write E. This is also say E, right? ANE is the charge. Now, equating these equations 1, 2, 3, what do we get? So we get E. This is V by M L into T tau. Right? this is equal to, say, I upon A N E. This gives us V as M, then L, then I, MLI, right? Whole upon N. This E into E becomes E square, right? Then tau T into area of cross section. Fine. Here we see, so M remains constant, L remains constant, N is the number of electrons, E is the charge on electron, and these all factors remain constant. So we have V is directly proportional to I, as we can see the physical conditions such as temperature, pressure, etc. They remain constant. Then parameters like say M, this is we have L, then area of cross section N, and of course E is charge on electron. E, they remains constant. Thus, therefore, V is directly proportional to I. So we may say V is proportional to I, which proves the Ohm's law. That proves the Ohm's law. Right? Now, yes. So we know that the ratio of electric field at any point within the conductor and the current density J, that's also called the resistivity. And we have discussed this, that resistivity is the characteristic property. It depends upon the, let's say, if, say, L equals to 1 meter, A equals to, say, 1 square meter, then rho resistivity will be equal to R. As per the formula, we have rho is equal to R A by L, right? So we can say specific resistance or resistivity is effectively equal to the resistance offered by a conductor of 1 meter length and area of cross section 1 square meter. 1 meter length and 1 square meter. So when the temperature of the wire or the metallic wire is raised, its electrical resistance also increases. Right? Its electrical resistance increases. Whereas resistivity of alloys, they increase with the rise in temperature, but that increase is smaller as compared to the pure metals. And resistivity of semiconductors, if we see, right? The increase in the value of, say, temperature of conductors of semiconductors, they both are opposite. With the increase in the temperature in semiconductors, the resistance decreases. Fine. So today, that's all for today. So tomorrow we'll do the combination of resistors and Kirchhoff's law, which is very important from this chapter. Questions are asked from this chapter, right? So, bye. And that's all for today.